Hello student, myself Srimati Vidyavardhini Mule. My subject is physics. Today we are going to study 12th science chapter Superposition of Wave. In last lecture we studied the mode of vibration of air column in a pipe closed at one end. In this lecture we study the mode of vibration of air column in a pipe open at both ends. First mode of vibration, that is fundamental mode. In this figure we see that both the end of the pipe are open, so antinode is formed at both the end. There is more space to vibrate air, so here two antinodes are formed and node is formed at the center. So the length of air column is given as L is equal to lambda by 2, because the distance between two antinode is lambda by 2. So we get length of air column L is equal to lambda by 2. From this we get lambda is equal to 2L, where lambda is wavelength of fundamental mode and N is the frequency of fundamental mode. Then we know the velocity of vibration is V is equal to N lambda. From this we get N is equal to V divided by L, which is equal to, we know the value of lambda is V divided by twice L. This is called the fundamental frequency and it is called as first harmonic. Now in second mode of vibration, which is called first overtone, in second mode of vibration we see that here three antinodes are formed and two nodes are formed, and the distance between first antinode and last antinode is L is equal to lambda 1. So the length of air column is L is equal to lambda 1, where lambda 1 is wavelength of second mode of vibration and N1 is frequency of second mode of vibration. Then we know that velocity of vibration is N1 lambda 1, which equal to N1 is equal to V divided by lambda 1, which is equal to V divided by L, because value of lambda 1 is L. From this we get N1 is equal to twice N. This is the frequency of first overtone or second harmonic. Next one is third mode of vibration, which is called second overtone. In second overtone we see that there is 4 antinode and 3 nodes. So this distance between first antinode and last antinode is L is equal to 3 lambda 2 by 2. From this we get lambda 2 is equal to 2L divided by 3, where lambda 2 is wavelength of third mode of vibration and N2 is frequency of third mode of vibration. Then we can write V is equal to N2 lambda 2. From this N2 is equal to V divided by lambda 2, and from this V divided by value of lambda 2 is 2L divided by 3. From this we get 3V divided by twice L, and we know that V divided by twice L is known as fundamental frequency. So we can write here V divided by twice L is equal to N. So we get the value of N2 is equal to 3N. This is the frequency of second overtone and third harmonic. So एकत्रित त्याचं जर इक्वेशन बघितलं तर आपल्याला मिळतंय first mode of vibration, that is fundamental frequency, we get that N is equal to V divided by twice L. First overtone, which is called as second harmonic, we get N1 is equal to twice N, and that twice 2 is written as 1 plus 1 into N. second overtone, which is equal to third harmonic, that is n2 is equal to 3n, and that 3 is written as 2 plus 1 into n, and so on. Third overtone, that is fourth harmonic, is written as n3 is equal to 4n, and that 4 is written as 3 plus 1. In general, we can write pth overtone np is equal to p plus 1 into n. In general, for pth overtone, we get the frequency np as np is equal to p plus 1 into n. Thus, for a closed pipe, a pipe open at both ends, odd as well as even, both harmonic are present as a overtone. That means in open pipe, both harmonic are present, odd as well as even harmonic. Our next point is end correction. The distance between the open end of pipe and the position of antinode is called the end correction. Here in this diagram, we have given that distance between node and, or distance between open end and antinode. Distance between this open end of pipe and this antinode, that distance is called as end correction. This distance is called end correction, and value of this end correction is E is equal to 0.3 into D, where D is inner diameter of the pipe. That inner diameter is this diameter. Okay, this is the inner diameter of pipe, and that value of end correction is E is equal to 0.3 into D. For a pipe closed at one end, the capital L is equal to L plus E, which is equal to lambda by 4. L is length of pipe and E is value of end correction. So capital L is given as length of air column, and that length of air column, which is equal to L plus E. That L is corrected length of air column, small l is length of air column in a pipe, and E is end correction at the open end. For a pipe open at both the end, here for both the end, two end correction are formed at this point and at down point. Okay, so in between, this is the length of pipe, and in this diagram we see the two end correction at the both the end. So we get the corrected length of air column capital L is equal to small l plus 2e. 2e is end correction of the both the end, which is equal to lambda by 2. Vibration produced in a string. Before that, we study the vibration produced in an air column. Now we are studying the vibration produced in a string. Here we consider the first mode of vibration, and here we get only one cycle, that is 2 node and 1 antinode, and the distance between 2 node we know that, which is equal to lambda by 2. Therefore length of string L is equal to lambda by 2. From this we get lambda is equal to twice L, and we know the velocity of vibration, velocity of oscillation, which gives V is equal to n lambda. From this, n is equal to V divided by lambda, which is equal to 1 upon lambda into V, and value of 1 upon lambda is 1 upon twice n, and value of V is given as under root T divided by M. This is the fundamental frequency, and it is also known as first harmonic. Now first overtone or second mode of vibration. In second mode of vibration, we get the length of string is equal to lambda 1, that is L is equal to lambda 1. So we get the equation velocity is equal to n1 v1 n1 lambda 1. Therefore n1 is equal to v divided by lambda 1, and we know the value of 1 upon lambda 1 is 1 upon L, and value of v is under root t divided by m. From this, if we multiply numerator and denominator by 2, we get the value of this is equal to n, and n1 we get n1 is equal to twice n. This is the frequency of second harmonic, or it is also called as frequency of first overtone. Next one, second overtone, which is called as third mode of vibration. The length of string, here the length of string is given as 3 lambda 2 by 2. Therefore from this we get that lambda 2 is equal to 2L divided by 3, but we know that V is equal to n2 lambda 2, so n2 is equal to V divided by lambda 2, which is equal to 1 upon lambda 2 into phi. Therefore we get n2 is equal to value of 1 upon lambda 2 is 1 upon twice L by 3, and under root t divided by m, value of v is velocity is the root t divided by m, which is equal to 3 into 1 upon twice L under root t divided by m. Value of this is n, so we get n2 is equal to 3n. This is the frequency of third harmonic, and it is also called frequency of second overtone. या तीनही इक्वेशनचं एकत्रित इन जनरल इक्वेशन आपल्याला कॅल्क्युलेट करायचं आहे. सो फर्स्ट मोड ऑफ व्हायब्रेशन वी गेट द व्हॅल्यू ऑफ n इज इक्वल टू 1 अपॉन ट्वाइस L under root t divided by m. Second, that is second mode of vibration, that is first overtone and second harmonic, we get n1 is equal to twice n, which is equal to 1 plus 1 into n. Second overtone, third harmonic, we get n2 is equal to 3n, that 3 is written as 2 plus 1 into n, and so on. We get general equation of pth overtone is np is equal to p plus 1 into n. The conclusion is, thus all harmonic are present as overtone in the mode of vibration on a stretched string. If we stretch a string and we produce our vibrations in that string, then we get that all harmonic are present as overtone. Thank you.